guess we can start. So welcome everyone. Welcome back. This is the first IRIM seminar in the fall semester. So it's really our great pleasure, including Professor Lu Gang and myself, to host Guanya for this visit. And Professor Guanya Shi is currently an assistant professor from Robotics Institute at CMU. He did his PhD from Caltech, and after that, he moved to University of Washington for postdoc. And Guanya has a lot of exciting, research topics, especially at the intersection of machine learning, control, robotics, and particularly, I think, focus a lot on how to design intelligent algorithms and these fundamental theories to achieve very agile robotics behaviors. And he also recently received multiple awards, including the well-known RSS, Outstanding Student Paper Award. And Guanya has a serious, exciting work very recently on humanoid robots, how to design this whole body control through teleoperation. I think some of you already saw this on the the social media. It's a very exciting result, how to design this very intelligent whole body locomotion manipulation skills, how to solve this RL problem. I think the same to real gap still a big and important question. There are a lot of things to explore. How to reduce the embodiment gap, this kind of thing are still a big question for robotics community. So I'll stop here and so let's welcome Professor Guanya Shi again, and look forward to the presentation. Thank you.
All right. Thank you, for the introduction. Very excited to be here to show you some of my recent work. I didn't expect to see so many people here. Thank you so much for joining me. Today I'm going to present a topic called Unify Semantic and Physical Intelligence for Generalist Humanoid Robot. Primarily, I'm going to present these three works in the first part. The one's called OmniH2O is basically we're trying to build some interface between human and humanoid motions. And second word is called WoCoCo, which is basically a reinforcement learning framework that can learn a versatile loco-manipulation skills. Last one is called Agile but Safe, which is a safe navigation and agile method for a quadrupedal robot. Okay, I'm going to start from some introductions. Many people say 2024 is the year for humanoid, and this is just like a partial list. You saw a lot of companies here. Apparently, I didn't include all of them. It's just like a partial list. So why? Why it become so popular, and why many people believe in humanoid? I think a common belief is humanoid is a promising physical embodiment for general intelligence in the real world. And there are two kind of like common arguments. So the first argument is humanoid are built as general purpose robot. For example, this is some like demos from my lab. You can see it's one robot, the same robot, Unity H1 can do a lot of different tasks. It can play sports, play tennis. It can do this like a loco-manipulation, long horizon task, can move the basket to the cart and move the cart. It is a pretty long horizon loco-manipulation task. And it can also do some entertainment for us, like this clapping dance. And also it can do this kind of parkour jumping. In this video, it kind of jumped twice on the stairs. So you can actually argue in all these tasks, there exists some robot maybe better than humanoid. But I think the common argument is humanoid is general purpose, right? It can do all of them. Yeah, this is argument one. And the second argument is the minimum gap between human and humanoid, the embodiment gap, is really great. It suffers a couple of advantages. For example, it potentially enables scalable data collection, right? We can directly use the data from internet, human data, we can directly use the human data, like human video, things like that. And also, right, we don't need to build new infra in the real world, right? Because the real world is designed for human. The humanoid should also work. And another, right, psychologically, right, it's pretty natural to partner, right, with people, right, because they have the same morphology. And just give you some examples. This is some teleoperation procedure we did in the OmniH2O project. You can see it's very natural. you can move your hand. The humanoid will move your hand. You can move your finger. You can squat, right? The humanoid will squat. This is something like standard mobile manipulator cannot do, right? You have to have a torso to have this squat kind of like behavior. And the rat video is related to human-humanoid interaction. This is actually enabled GPT-4o. We integrate our controller with GPT-4o, and GPT-4o understand, okay, you want to shake your hand, and then shake a hand with a human. And then my student kind of want to hug, and the GPT-4o understand that. It asks the humanoid to hug you. Right? It's very natural for the human to interact with the humanoid. Yeah, this is basically two common argument why humanoid is so popular and useful and potential. And before going to technical details, I want to kind of talk a little bit about like taxonomy of humanoid intelligence. We can, like, there are many levels, right? We can all the way go from cognition level to reasoning, to planning, to motion skills, to control, all the way to actuation. And roughly speaking, you can classify this into three categories, right? The first category is called semantic intelligence, right? Basically means how the robot understands the physical world and make high-level decisions. And the second level we can call this is like a physical motion intelligence, right? Basically means how the robot generate useful motions, useful skills, right? And the bottom level we can call this mechanical hardware intelligence, right? Basically means like how the human actuate, right? And like Marco Ribert from BDAI will further classify this into two things, right? The first thing is called cognitive intelligence, basically like what should the robot do? And the second level is called athletic intelligence, what can the robot do? This is basically a taxonomy. And today's talk, we're gonna primarily focus on the middle layer and the connections between the middle layer and the top layer, and the connection between the middle layer and the bottom layer. So my argument is we have made a lot of breakthroughs in the top layer and the bottom layer recently, but we still have a lot of job to do in the middle layer. I'm gonna give you some examples, right? Why I said there are a lot of breakthroughs in the top layer and bottom layer, that is because the foundation models and hardware, right? As we know, there are a lot of like recent exciting research integrating multimodal frontier models and robotics. For example, this is like kind of like a very popular video, like collaboration between Figure and OpenAI. Yeah, so this is actually a pretty simple task for human, but like even we go to 3 years ago, right? It's kind of like very hard, right? Because to do that, the human now need to understand semantically what do you mean by eat, right? And then need to understand the word, right? Need to understand on the table, apple is the only edible items, right? And then I need to deliver the apple to you. It's like pretty complex and semantic kind of task, right? And similarly, right, we have a lot of like robotics foundation models, like robotic transformer from Google DeepMind, for example. It can understand semantically what do you mean by move the soccer ball to basketball, things like that. And also, right, I would argue at the bottom level, we also have a lot of breakthroughs. We have a cheaper and better hardware. Every day, you're seeing some new and cheaper humanoid. For example, this is a recent humanoid from Unitree called G1. It's pretty cheap. Even cheaper than GPU. You can purchase a pretty good humanoid, right? That robot here can do a lot of different things. Like it can do a lot of like this I would argue this is a superhuman motion skills, and can walk, can do a lot of like this robustness task, and also you can even use that to open Coca-Cola, right? Yeah. So my argument is, right, we have a lot of breakthroughs in the top and the bottom layers, but the middle layer, which is physical intelligence, seems still pretty hard. For example, this is a well-known like failure case from BD's Atlas, right? And this is interesting in not a perception problem actually, because they have like QR bar on the objects. Basically, in this case, there's no feedback. The robot doesn't know it didn't catch the card. It thought it catch the card, but it didn't, so it fell. All right, and similarly, right, in our OmniH2O, we have honestly a lot of failure case. For example, in this video, it's a locomotion failure case. It works well on the concrete road, and it didn't know it went to this grassy road, and it just fell, right? And another example is, as I mentioned, humanoid with teleoperation is pretty smart. And this is like a video like with human brain, with teleoperation. Humanoid is pretty smart. It can solve this long horizon loco-manipulation task. You can move one basket to the cart, and you can move another basket to the cart and move the cart, right? It's pretty good with human teleoperation. Like 10 times trial, we can succeed at least 9 times. However, we try to make it autonomous so hard. Like humanoid with a human brain is smart, but humanoid itself is still pretty kind of stupid in physical intelligence. So I'm not going to answer the question why it's hard and solve this problem, but hopefully I can give you some insight. And today's talk is 2-part. So part 1, I want to cover some recent humanoid quadruped research based on sim-to-real RL. And we're going to cover, again, the middle layer and the connections with other 2 layers. More precisely, we're going to first do human to humanoid, which is, again, an interface between semantic and physical intelligence, because we want to develop a versatile motion tracking controller that can track any desired motion from the top layer. And then I'm going to present something called a WoCoCo, which is basically a reinforcement learning framework that can learn versatile motion skills. And then I'm going to present something called ABS, agile but safe. So basically, the argument is if we really want to push to the hardware limit, and we have to consider safety. Because if you want to have really agile robot in the real world, you have to make sure it's safe. Yeah, this is the part 1, 3 project related to sim-to-real RL. And then I'm going to do some reflection to discuss the limitation of sim-to-real RL and how to go beyond it, because there are apparently many fundamental limitations. And a very interesting questions for all of us, do we still need model-based control? Okay, this is 2-part. All right, let's get started. So I'm going to start the H2O project, which is the acronym of human to humanoid. The goal of this project, the high-level goal is we want to build an interface between human and humanoid emotions. And specifically, in this project, we want to use a single RGB camera to whole body tailor up a full-size humanoid. So before talking about the details, I'm going to play the video, which is like basically a teaser. It can do like step forward and punch. And this is the whole body task, right? It's not just upper body. And the kick, first the left feet and right feet, and the right and left. You can switch the order because it's whole body control. And you can grab the box and drop it in trash bins, box hand over. And it's moving and then boxing, and moving and then boxing. Yeah, and human pose walking. And some back jumping. Some more boxing stuff. And more like a step forward and punch. And we try very harsh in boxing. And walking a stroller. I guarantee there's no baby inside, it's just a stroller. Yeah. And to publish humanoid paper, you have to bully the humanoid to prove your method is robust. So we did that to show it's pretty robust in terms of control. You can even fly kick it and push it, etc. Yeah. So this is basically the result. So before I talk about details, like why is it hard? Since like teleoperation is not new, right? People have done teleoperation for all kinds of robots, especially for tabletop manipulation. So what is the delta like humanoid has, right? So it is hard primarily 2 reasons. The first is we need a robust and stable whole body control. Okay, it's not just like upper body or lower body, it's the whole body, right? We need to consider the upper lower body coordination. And the second, right, we need to track a diverse human motion in real time, right? We need to track infinitely many possible human motions. So these 2 make this pretty hard. So how do we solve this? So the key idea of H2O is sim-to-real RL from large-scale retargeted human motion dataset. That's a 1-sentence summary of the project, basically. Yeah, and there are like 3 steps. The first step is to create a large-scale human feasible motion dataset. So we start from some existing human motion dataset called AMAS. It's basically a large archive of existing human motion dataset like this. It has a lot of diverse human motions. And the question is, can we simply do inverse kinematics to convert this AMAS dataset to humanoid shape? Right? People do that all the time in other robot like manipulator. Right? What do I mean by inverse kinematics is we basically find some SMPL model that is closest to our humanoid, and you do simple inverse kinematics from here to here, right? Can we just do that and the problem is solved? And the answer is no, right? Because if you think about this, like some motions here are invisible for the humanoid. And it's either invisible or like weird. For example, this kind of like motion, right? It's very hard for a human to do that. So we need some kind of like pre-processing or some filtering. So the procedure we did is actually pretty simple and intuitive. We did a procedure called simulation-based data cleaning. So how do we do that is we train the pink policy here. It's a privileged imitation learning, sorry, not imitation learning, my bad. It's a privileged imitation policy to track all the motions. So this is a pink policy here. So what is really important is this policy is privileged. It has access to all possible robot states, including those not necessarily available in the real world. For example, it knows everything. It knows all the joint angle, joint angular velocity, angular acceleration, all the kinematic poles, everything, right? Many of them are actually not available in the real world. It's why it's called a privilege, right? And we use this policy as a filter to filter out impossible motions and to do the retargeting, right? This data set at the bottom, right, is the final data set from this procedure, right? You can view this procedure as at least we need to select some motion that is possible, right? Remove these impossible motions. That's kind of the idea. This is a step one. So step two is called sim-to-real RL training, right? So step two is we're gonna train this blue policy in simulator, right? And to track previously mentioned retargeted data set, right? And in particular, in this project, we choose to use 8 key points as the motion tracking goal. The 8 points is, as you can see in this photo, is 2 elbow, 2 shoulder, 2 ankles, and 2 hand. These are 8 key points from the human pose. We train this policy to track these 8 key points. So the important thing is compared to the privilege policy, this policy only uses realistic robot states that is available in the real world. We remove all the kind of privileged information and only use realistic information. And also, as you can imagine, we did tons of like robustness method to make it seem to real. For example, we did a lot of randomization, a little bit of system ID, things like that. Yeah, this is the second step. To summarize, we want to train a deployable policy that can do seem to real transfer. Yeah. And once we do that, the third step is pretty straightforward, just like real-world RGB-based tele-op deployment. So we use an existing framework called Hybrid, use RGB camera to estimate this kind of human pose, basically a point cloud. Once we have this human pose, we just use our deployable policy, the blue policy here, to track the 8 key points from this pose. Right, this is the real time. The RGB part is 30 hertz. The controller part is 50 hertz. The low-level control is 200 hertz. Yeah, this is a whole procedure. It's pretty straightforward, I actually think. To summarize, 2 steps. The first steps, we need to do some retargeting to convert human motions to humanoid feasible motions, right? To convert the top motion here to the bottom motion here. And the second step is sim to real, right? We need to train the blue policy here that is deployable in the real world, and that can do sim to real transfer. And the last step is just deployment, which we can do RGB-based teleoperation. Right. And there are a bunch of limitations. Like first, maybe you already noticed from the video, there are some latencies, like roughly speaking, 300 to 500 milliseconds, mainly from the RGB camera. So the RGB camera is real time, right? It's 30 hertz, but the latency is pretty large. And also, right, this procedure requires a lot of information from human. It requires 8 key points, right? 2 shoulders, 2 elbows, 2 hands, 2 ankles, right? In many devices, you actually don't have access to all of them. For example, if you use VR, like Apple Vision Pro or like Meta Quest, you probably don't have access to ankles, right? Or shoulders. And also, like, apparently in the video, we don't have hands. It's just a humanoid. And also, we don't have autonomy, right? It's purely teleoperation. So we basically fix all these issues in a follow-up with project called OmniH2O. The Omni here stands for universal. Basically, in this project, we build a universal and a dexterous human-to-humanoid teleoperation and autonomy procedure. The key point is we enable low latency and precise teleoperation with dexterous hand. And this new framework enables pretty diverse interface, not just RGB. We can also do VR, like Apple Vision Pro here, and verbal instructions. And also, more importantly, we can do autonomy, either from imitation learning, from the human demonstrations, or we can integrate with foundation model like GPT-4o. Okay, as usual, I'm gonna play the teaser video first. This is a one-shot. This is a one-shot video. In the whole video, we are using one single neural network to do all the control. Right. Again, this is a whole body control problem, right? You need to jointly control the hand, upper body, and the lower body. It's gonna move to the workstation and start doing some interesting tasks. Yeah, it's gonna grab the knife. I'm sorry, it's a little bit scary, but it's going to cut a cucumber. Yeah. Yeah. And this part is purely teleoperation. And then say hi to you, and the robot is gonna step back and start sweeping the floor, clean the room a little bit. Step back and clean the floor. Right? The key point is like, again, it's general purpose, and it's whole body control, and it's single policy. Real-time teleoperation, right? And say hi to you again. And we can do a lot of tasks like this. All this manipulation, watering the plant, moving basket, many different sports: tennis, table tennis, ping pong, all whole body. And we can also do like boxing, drawing, and squatting, all this different stuff. And this is like what I said, right? Integrating with GPT-4o, it can create with human, say hi to you. And this is imitation learning. This is from like teleoperated data. We can do imitation learning, can do autonomous policy. Yeah, and this is a verbal instruction. We can literally talk to the robot. Can you move to the left side? See you next time, bye-bye. The robot can correspondingly react. And again, we bully the robot to answer reviewer questions. And it's pretty robust. And also we can, single policy, same policy, we can do outdoor locomotion. That is pretty robust. Yeah. All right, this is the project. I'm sorry I played this video very fast. I know that. If you want to check out more videos in the website. Okay, so the main technical change from H2O is actually not too many, honestly. We have three main change. The first change is we augment the AMAS dataset with more standing and squat motions. Like we add more or less kind of C and D motions in this figure. Right? We add a lot of like standing and the squat motions just to make it more stable, to make it better for manipulation task. And another thing we change is we give up on using RO to train the student policy. We use teacher-student framework with imitation learning to learn the deployable policy. So what do I mean by that? If you remember previously in H2O, we first use RO to train this red privilege policy, and then we use another RO to train this blue deployable policy. And in OmniH2O, we only use RO for the red privilege policy, and we use imitation learning dagger to distill this red policy to this blue deployable policy. And we found it's much more stable in terms of training, and it can generalize a little better. It also makes debugging much easier. Yeah. And the third difference is, in this project, again, we want to enable diverse interface, right? Not just RGB, we also want to use VR, so we use only 3 key points as the motion tracking goal. Right? Previously in H2O, we use 8 key points, right? And here we only use 1 head and 2 hands. It's just 3 points, 3 key points from the human pose for the motion tracking. And the hand part is separate. The hand part is just we got this like a finger postures from Apple Vision Pro, and we just do inverse kinematics. This part is pretty separate and standard. All right, this is the main technical change. And what it enables is, again, right, once we have this stable, precise teleoperation procedure, we can enable data collection, right? And so we collect some interesting data, and we release, I believe, the first humanoid whole body demonstration data set, and you can check out the QR code. And basically, it includes 6 pretty diverse whole body tasks. In all these tasks, right, the humanoid need to do some upper lower body coordination. And with this data set, as you can imagine, you can do something called imitation learning. And in this video, we actually train a policy using diffusion policy to kind of like do this task automatically. And this is moving the hammer from one basket to a ball. Yeah, it is autonomous. I didn't take we didn't take a video of the lower body, but the lower body is not doing nothing. It needs to support the upper body. Yeah, that's the key idea. Yeah, this is the data side and imitation learning procedure. And as I mentioned, right, once we have a general motion tracking solutions, we can immediately integrate it with any semantic layer, for example, foundation models. And in this case, right, and again, because a humanoid is very similar to human, the prompting is actually very simple and straightforward. You literally tell GPT-4o, okay, you are a humanoid robot equipped with a camera, blah, 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 and this is something you can do, how many degree freedom you have, like, you know, we basically ask GPT-4o to do a multi-choice selection. And in this case, right, as I showed previously, it can you know, shake hand with you. And it's multimodal, by the way. We real-time send the photo to GPT-4o. Yeah, it's not just text. And GPT-4o, you know, you want to hug, so yeah. This is. So you probably notice like 1 to 2 second delay. It's not because the controller is we are waiting for API's response. So if any of you work on efficient like VLM, the real-time VLM, that's going to be very useful, I think, because yeah, that's the bottleneck right now. Yeah. All right. This is the H2O part. I can take a quick questions but maybe I can do it later. Yeah, go ahead.
So when you're doing the inverse kinematics, how do you account for similar motions that have different forces? For example, if I'm placing my hand on the table versus actually pushing on the table.
Yeah, that's a very good question. So the inverse kinematics here is we are doing some gradient-based method. So indeed, first, it doesn't guarantee convert to a global minima. And second, I want to mention a big limitation, in my opinion, H2O is in the data side, we didn't consider any object interaction. So we cannot reason like how much force it pushing the object or something like that. This is entirely done by human feedback. Yeah, cool. Okay, I'm gonna switch to the next project. We're going to open source the code, all the code from hardware to software H2O very soon, probably in this week, and just, you know, take a look, yeah. Okay, the next thing I wanna present is called WoCoCo. This is actually another extreme. In H2O, the goal is to learn from human. And here the goal is to learn without any human preference, right? Because in many scenarios, the robot doesn't actually have any human motion reference. So the goal of WoCoCo is, again, we want to learn versatile humanoid robotic skills without any motion prayers. As usual, before presenting the technical details, it's just some teaser stuff. Yeah. And the robot here can do parkour pretty well in simulation, and it can transfer partially to the real world. Much simpler, unfortunately. It can do this continuous jumping over stairs, and it can also do this, again, very funny clamping dance. We actually have a background music, but it's a little bit stupid. I don't know should that or not. Yeah. Anyway, yeah. I can also do like interesting bad directional cliff travel. So again, we want to show like upper lower body coordination, right? If you want to, yeah. And this is like a loco-manipulation. We can move a box from anywhere to anywhere. Like the robot can grasp a box and move to another point. Yeah. It's again, I played this very fast. Tons of videos. Check out the website if you're interested. But I want to give you some insight how it works. So the key challenge of learning this context-rich local manipulation skill using RL is, unfortunately, you will understand this sentence deeply if you are a grad student working on RL. You have to tediously design different reward function, task-specific reward function for different tasks. Like different tasks either use very complex reward function or strong motion priors, right, like H2O. This process is not very interesting. Nobody likes tuning reward function for RL. So the key idea of WoCoCo is we realize a lot of context-rich local manipulation tasks actually can be decomposed as a sequence of context goals and task goals using context. So here's one example. Remember the parkour jumping stuff earlier in the video? You can actually decompose this long horizon motion into 5 stages. Right, and each stage, you can assign a context goal and task goal. For example, in this particular stage, The contact goal is you only want the right foot establish contact with the stone. You don't want the left foot in the air, right? This is a contact goal. Is how many in the effector establish contact with other object or the environment. And we also need to define a task goal. Right, the task goal in this setting is we want the upper body posture maintaining certain, like, in this case is kind of like a hug. You can also do relax. If you see actually in this video, sometimes it's relaxing, sometimes it's a hug. It's on purpose, right? So basically the idea is we can decompose this long horizon stuff into a sequence of contact goal and task goals. By the way, the contact goal is not limited to lower body. You can also do the upper body contact goal, like grasping a box or something like that. Okay, what is the advantage of this decomposition? Is once we have this decomposition, again, this is a visualization, we can decompose a task into a sequence of contact stage. Each stage includes a contact goal and task goal, right? And the advantage is we can just learn a condition policy. Right? This policy pi is a function of state, and it's conditioned on sequence of contact goal, G contact, and a task goal, G task. The I is the current stage, and the big I is the last stage, right? And what is the advantage of this representation is it enables very easy reward and training design. More precisely, it enables task agnostic, like reward design, training design. So all the tasks you see in the video, from like parkour jumping, from dancing, they share the contact reward. The contact reward and the symptom reward are shared for all the tasks. The only different things is for each task, we only need to add one or two reward terms related to the task goal. Yeah. So basically, the key idea of WoCoCo is we do this decomposition, and we have a pretty simple and generalizable representation, which is a sequence of contact goal and task goal, and that enables super simple reward design. They share contact reward, they share sim-to-real reward, they share regularization reward. The only thing tasks are different is the task reward, the task goal reward. Yeah. Unfortunately, I'm not going to training details, everything, but this is like the key idea. Check out the paper if you're interested. Okay, I want to move to the third topic in the part one, which is safety. The reason is we realize if you want to fully unleash the hardware capability, that requires safety. We have some video collections of all the failure cases in the WoCoCo project. And here's a failure case, right? And humanoid is general purpose, and unfortunately, it can also give you all kinds of failures. Sometimes it's just a fail, sometimes it's just like, it's all the weird things, right? Without a safety guard, the robot is either too conservative, not useful, or too fragile. So we are working on humanoid safety, but today I want to give you some preliminary result on quadruped. Like one popular approach for safety in control is model-based safety filter, right? We basically use the dynamics model to derive an analytic filter to ensure safety. For example, control barrier function. And this is some control barrier function research from our group in last year's ICRA. So the idea is the pi theta here, the pi theta is potentially unsafe reinforced learning action. And you want to filter it out using this quadratic programming, right? You need like this F and G are learned dynamics, right? You want to kind of design this QP program to filter the potentially unsafe RO action. So if you think about how to apply for Lego robot, I think there are two problems. The problem is like this procedure need to explicitly learn an accurate dynamics model, right? Here we need to learn F and G and assume it's control F1. But Lego robots in general not a control F1, and it's hard to learn explicit dynamics model. And second, right, this is not very scalable with high-dimensional sensory input. For example, if you want directly guarantee perception-based control safety, and this is pretty hard. So the goal of this project, ABS, is the key idea is we want to do a model-free way. We want to learn a rich avoid value function to safeguard the vision-based locomotion policy. And again, this is entirely model-free. It doesn't need to know the model. It only needs to rule out the policy in some black box dynamics model. And this project is fully open source. So if you're interested, check out the QR code here. And as usual, just some teaser videos. And the robot here, we can enable, it's fully on board and autonomous. Robot is very fast, up to 3 minutes per second. And it's very safe in terms of collision avoidance, can walk in narrow cluttered corridor. The video is real time, didn't speed it up. And it's also very robust in different, it's winter Pittsburgh, it's pretty cold compared to Atlanta. And it can be pretty robust on grassy terrain, things like that. Yeah, this is indoor in NSH at SAMU, NSH building. Okay, I'm gonna skip to my favorite part. Yeah, it can like basically collision volumes. Here, yeah. So the human it's very real time, right? You can swing your leg. The robot can just dodge. It's very real time. Yeah, and you can even play this hide and seek game. Yeah. So one thing I want you to pay attention to is sometimes the LED on the robot is green, and sometimes it's red. It means we are running two policies. One is called agile policy, one is called recovery policy, which I'm going to go through in the next slides. So how do we do that? So basically the idea is, so given a potentially unsafe agile policy pi, what we do is we use policy evaluation to learn a reach avoid value function v pi to quantify a safety level. So this v pi RA can be efficiently learned via this reach avoid Bellman equation. This gamma here is a discount factor, and zeta is some function quantify safety. It's negative if and only if it's safe, and L is some function quantify the reach. It's negative if and only if the robot reached the goal. And this V as pi as a dynamics model, right, is next state. But the interesting thing is you don't need to know F to do this like a policy evaluation. You just need to rule out pi in the black box simulator. And also this is guaranteed to converge because it's a contraction. This is a contraction mapping in terms of L infinity norm. Right, and this is some visualization of the learned value function. It kind of makes sense. It's basically a fancy version of potential field, if you're familiar with planning, right? Like you can see in these figures, the green means safe, and red means unsafe. And if you change the velocity, change the orientation of robot, you have different safe and unsafe state. Yeah, and as you can imagine, once we learn this v pi, you can use that as a safeguard for pi. So basically, what happens, as you can see in this figure, is we do a kind of like two policy switch. So if the value function is negative, that means the robot is safe, and you just execute the agile policy pi. And if the value function is positive, that means the pi is unsafe. So we switch to this red recovery policy. The goal of the recovery policy is to lower the value of v pi. So that's basically how we close the loop. That's basically set up. The key idea is we use a model-free way to learn v pi that can quantify the safety level of the agile policy. And then if it's unsafe, we switch to recovery policy, which can lower the value of v pi. That's the key idea. All right. I think I finished the first part. You probably, there's some interesting videos, right? All the demos in part 1 are trained with model-free sim-to-real RL, right? They're all trained in the same procedure. You have some way to build a simulator, you train a policy, and you do zero-shot sim-to-real, right? And the question I want to discuss is, do we still need model-based control? Is this sim-to-real RL pipeline good enough, right? I mean, from video, it's pretty cool. But there's some like fundamental limit we found in this project. Some of them we include in the paper, but some of it are not in the paper. So basically, right, I really think if we only rely on sim-to-real RL, we will quickly reach to some limit. For example, right, the policy are very sensitive to training environment. Like you change like single simulation parameters, the policy will change a lot. Even you change the seed, the policy will change a lot. Like some seed give you robust policy, and some seed give you like weird policy. And the sim-to-real gap is never going to be 0. And even worse, it's hard to quantify. We don't know how large is sim-to-real error. We don't know which robot, which state gives larger sim-to-real error. Right? And as I mentioned before, this procedure in general requires very tedious reward curriculum randomization tuning, which nobody likes it. Yeah, and also it's hard to encode prior physics, right? And they suffer from very poor sample complexity. And it's hard to get a guarantee. Even though you have a guarantee, it's hard to verify the assumption. For example, in ABS, technically we do have guarantees, but it's guaranteed need to assume, right, that the value function in learning is same, is absolutely close to the value function in the real, and you also need to assume the recovery policy is good enough, things like that. It's very hard to verify these assumptions in simulator. Yeah. So how do we address these issues? So another topic I really want to present today is, can we possibly combine the advantage of model-free learning world and the model-based control? Can we have best two worlds, right? And this is basically the connecting learning control. And apparently today I'm not going to very deeper in this topic, but I really want to maybe give us some insight to give you like 3 common ideas. This are not my ideas, very common in the field, right? Roughly speaking, you can do these 3 different types of learning plus control, right? The first step is dynamics level, right? You can use learning to learn dynamics, right? You can learn dynamics from real world. You can either learn residue or full dynamics. And the second level is action or policy level, right? It's something called structured RL and control. Like rather than doing end-to-end RL, we can add in some structure to the reinforced learning to make it better. And the third level is program level. It's neither learning policy nor learning the model. It's like using learning to enhance or accelerate model-based control. Yeah. Okay, again, as I said, I'm not going to detail, just some examples. So for dynamics level, it's probably the most straightforward. One example is my PhD work called neural control family. The idea is, okay, we have this standard Euler-Lagrangian, right, rigid body dynamics model, and there are some residual terms which is not covered in the simulator, right? And what we can do is we can collect real data to use a neural network to approximate this unknown dynamics, right? We call this F hat, right? And we did this in a single agent called neural lander that can land a drone against, ground effect. And we also do this multi-agent, right? And the residual dynamics is the interaction between different drones. And we also do this in terms of adaptive control, right? And in this case, F is aerodynamics, the wind, right? The aerodynamics from wind, right? It works pretty well for drones because in drone it's pretty easy to learn F because it is continuous. However, how do we do that for legged robot, especially humanoid robot? How do we learn residual full dynamics for humanoid? I think it's pretty hard. So basically, I think it's a real to same problem, and it's relatively doable without context switch. However, with contact, this is a hybrid, it's become pretty complicated. And we are working on that, and there are some like preliminary results. And first, I want to show you like there's indeed a very large symmetrical gap. This is like same motion in simulator. We want to do the pitch angle up and down. You have this symmetric kind of motion in the simulator. In the real world, it's not even close, right? And we found that part of the reason is the gap between the motor dynamics, right? Like ideally, you want the command torque is the same as the actual torque, but in reality, you have these nonlinear relations. And this is like just one example of why real to same learning dynamics could be helpful and is important for like a locomotion. And yeah, this is learning dynamics. And the second idea, as I mentioned, is learning policy or action. Again, the idea is rather than doing reinforced learning end-to-end, we can do structured RO and control. And this is one example called Cajun and follow-up. So the idea is, okay, when we control a robot, especially a legged robot, we don't have to do end-to-end RO, right? In this case, we use reinforced RO to output centroidal level information, right? The RO here is only outputting the desired velocity, desired angular velocity, and kind of like swing-like trajectories for the robot, the brown part here. And we use a QP, quadratic programming, to solve the GRF, which is ground reaction force. So this part is a QP, right? And once we solve ground reaction force, we use whole body control, which is another model-based control layer to solve the torque. Right? The idea is we use kind of reinforced learning only for high-level motion planning, and use model-based control, especially like QP-based control for the low-level kind of optimization. And it's working pretty well. You probably saw a lot of like model-free RO parkour paper, and we did like even harder parkour that is continuous jumping. For example, here we can do continuous jumping over stepping stone, right? This is actually require very precise control, right? Because it's not just like jumping once, it's continuous jump over this kind of like stepping stones, right? And we can also do this, this robot can adapt to the jump, right? The gap, if the gap is too large, if you jump to the ground first, and if the gap is like okay, we'll just one-time jump. Also, by the way, the RO policy here is perception-based. So we directly like feed in the perception information into the RO policy. So RO policy do know like when they need to jump. Yeah. I also think for the first time, we can finally enable something our dog can do, right? Continuously jump on the stairs. Okay, it's very easy for quadruped to walk on a stair, but for continuously to jump over the stairs, still pretty complicated. And our method can do that. For example, you can see here, my favorite part, the robot can do self-corrections. If you can see the laser point, right? Here it's actually about to fail and it can correct. It's really because the robot is from QP. The QP layer is kind of, in this case, the only thing it does is to drag the robot back, right? This makes the procedure very robust. And also, we can reduce the sim-to-real gap, yeah. And again, in this video, it's continuous jump, right? The robot can continue to jump over a 80 centimeter kind of like a stepping stone, yeah, stage. Right. Okay, another benefit of using this hierarchy I forgot to mention is, remember the real to sim stuff, right? Once we have a real to sim, we have a better model, then it can immediately go to this model, right? Like, for example, if you have better like mass inertials, that go to A. If you have like better gravity, that goes to G. We can do like the real to sim learning dynamics can directly go to this QP procedure. Yeah. All right, the last part of my talk. Again, I mentioned like certain ideas combining learning control, learning dynamics, and learning action. There's another thing you can do. It's neither learning dynamics nor learning policy. This is called learning program. So basically, we are not trying to replace model-based control. We are trying to use learning to enhance model-based control. For example, we can use learning to accelerate or enhance something called MPC, model-predicted control. So if you're not familiar with MPC, MPC is basically an optimization control approach. At every time step, you need to solve these pretty complex optimization problems. Where, for example, you have a drone track a trajectory. You need to like minimize your distance between X and the future waypoint subject to dynamics, right? This is like commonly known technique in model-based control. In my opinion, this procedure has two main disadvantages. If we think about the comparison between MPC and RO, it's not fair because MPC doesn't leverage any offline computation. All the computation of MPC is online, right? It's not a fair comparison with RO, right? Because RO can spend forever offline to learn a policy, right? And also, right, as I mentioned, this problem is potentially very non-convex. It's in general very hard to efficiently solve non-convex problem in real time. Because we want it like as fast as possible, right? Something like 100 hertz or 50 hertz. Yeah. So I want to give you two examples, like how to use learning to make this program better. And the first example is we can actually learn a residue optimizer for sampling-based MPC. I guess because at Georgia Tech, some people here should be familiar with MPPI, which is the most famous sampling-based MPC algorithm. So MPPI is doing great, but to make it better, basically what we learn is some residue optimizer to make MPPI better. So more precisely in this paper, we learn a shift residue modular and optimizer residue. So in standard MPPI, you just like shift previous solution by one step, right? And here we allow more like interesting, more nonlinear shift. And here in standard MPPI, you do this kind of softmax, right? Kind of like update. And here we enable some residue, right? I want to emphasize these two green blocks, they don't directly output action. They output like certain way to influence this MPPI program. It's why I call it program level. And it works pretty well. For example, in this very challenging drone flipping task, drone like yaw flipping, you basically want to, the yaw angle of the drone flip like 180 degrees. And this method is much better than MPPI with much fewer samples, right? The key idea is you can use RO, you can use any learning to kind of enhance this algorithm. Okay, the last paper I'm going to show you in today's talk is you can use something like diffusion to help trajectory optimizations. So in this paper, the idea is we borrow the idea from diffusion model, right? In standard like sampling-based TO, right? What you do is you literally sample from the same distribution. Like for example, if you do shooting method. And here we have some inspiration from diffusion model. What we do is we have a like forward process to gradually crop the optimal trajectory. And we have this backward process, right? We can like iteratively refine this trajectory. And the important is this procedure is model-based, so we computed the score function, right, which is something you need to compute when you do this backward process. We compute this using model information rather than from data, right? This is basically like kind of like we use diffusion style annealing procedure to enhance sampling-based TO. And this works pretty well, especially for this contact-rich task. We can, as in the beginning, the trajectory is pretty messy, and we can iteratively refine to this kind of like pretty okay motion from scratch. It's entirely solving a long horizon TO from scratch without any motion priors or any data. Yeah. All right. I think I'm gonna conclude here. So summarize my talk today. In part one, I present some recent humanoid and quadrupedal research based on symmetrical reinforcement learning. I cover 3 different things. In H2O, the goal is we want to build an interface between semantic and physical intelligence by building a general purpose motion tracking controller for humanoid. And in the middle level, I present WoCoCo, which is basically a reinforcement learning framework that can learn versatile motion skills. The key idea is you can decompose a long horizon loco-manipulation skill into different context stage. And also present how we do safety, pushing the hardware to the hardware limit while like maintaining safety in a model-free and a scalable way in ABS project. And in part 2, right, I mentioned some limitations from the symmetrical pipeline, and I quickly mentioned some potential ideas to get best of model-based control and model-free learning. Right, the first idea is you can do dynamics level, you can learn residual full dynamics. And action policy level, you can encoding some structure to reinforcement learning. And in the program level, you can use learning to enhance or accelerate the model-based control program. Okay, thank you so much, and I'm ready to take questions. Yeah.
Okay, all right. Yeah, thanks, Guanya, for the very nice talk and also the nice discussions at the end. Before we take questions, I just want to send a short note. For students who want to have lunch after this seminar with Guanya, we have a room change. So it's going to be the class atrium. So it's the seminar, usually the IRIM seminar room in class building. Because we have more students want to join, so the original conference room is not big enough. If you don't know where it is, you can just come to the stage after the seminar, so we can show you where it is. Okay, so now we can take questions. Yes,
yeah.
Shreyas.
Sure. Thank you for the exciting talk.
Thanks.
Good to see lots of videos of robots. I want to understand more. I had 2 questions.
Mm-hmm.
First, from the WoCoCo work, you're claiming, I guess, I want to understand more what you mean about the specifying the contact sequence as the key idea. I mean, like, how is isn't that what the humanoid motion planning was doing before, or like what's the
yeah? It is actually, this idea is not new. It's commonly available in model-based planning approach for humanoid. But I think this is the first time we do that for design RO framework that is compatible with that. And also, this decomposition, we don't learn it. We assume it's a human or other program design is for you. So that part is not autonomous.
I see. So it's
yeah.
kind of like the same as like Boston Dynamics is doing, but instead of MPC, you're using RO.
Exactly. You can. Yeah. The key idea is we found how to make RO efficient with this decomposition and make it work. Yeah.
Okay. Relatedly, so in ABS, the ABS thing is really cool, right? Like the robot is sprinting around. I want to clearly understand what you mean by model-free safety. Like what?
So model-free safety, I mean, when we learn the safety filter, we don't need to analytically know this function f, which is dynamics. So all we need to do is rule out this policy in black box simulator. Yeah, I guess it's model-based in the sense that you still need some f to play with. But it's model-free in the sense that you don't need to kind of taking gradient or like knowing this function f. It just need to be a black box kind of simulator you can put your policy in.
So
yeah.
What is the safety specification? Or like how do you specify safety with either without the model or for the black box model?
So the safety specification here is this zeta function need to always be negative. Yeah, that's the definition. And we don't have like the guarantee is kind of vague here. Is like if V pi can converge to the true V pi, and if you don't have a symmetrical gap, and you do have safety, that like if your recovery policy can indeed lower the value of V pi, but we don't have verification if the value function is indeed the true value function, things like that. Yeah.
Sorry, I'm asking, I think, maybe a lower level question, which is like, literally, what does safety mean here? Like, are you training to
Sorry.
avoid an obstacle?
Yeah. The safety here, the zeta function in this paper is basically avoid all the obstacle in front of you.
With the center of mass of the robot?
With the center of mass of the robot. It's not whole body level. And we model the robot as a rectangular. We don't consider the leg level safety. You could. That basically make your zeta function even more complex. I think you're gonna suffer from a lot of symmetrical gap, things like that. Which you're gonna think is a limitation of symmetrical, by the way. Yeah. And also I wanna mention, we did a lot of like conservative design. In practice, not zero, it's some minus epsilon. And epsilon is, you can imagine is for robustness, right? Epsilon is, we make it more conservative than it's supposed to be. Yeah.
I see. Thank you.
Yeah, thank you so much. Yeah. Okay.
Just along the same point, so how long does it take you to compute this value function?
This is everything's real time. As you can see here, it's maybe small. You mean like online is very fast, 50 hertz, and offline training is like few hours. Yeah. Online inference is value function is a neural network, 50 hertz. Offline training it takes few hours. Yeah.
But that's a challenge. But if you constraint changes, if the obstacle of the shape changes.
Yeah. So this in the theory part, the theory part we assume quasi-static. Like the zeta function is not a function of like it's only a function of robot state. Yeah, but if you do a dynamic object, I think you need to do something more. Probably some game theoretic approach or something like that. Yeah.
And then the reach region, where is it?
So the reach what?
So this is the reach avoid formulation.
Yeah.
And what's the reach region?
Oh, the reach part is like, okay, the safety itself is not enough. If you only consider safety, like sometimes the robot will do safe, but useless behavior. So we need to also consider reach part, like basically we need the robot reach the goal. So basically, this project is point A to point B and avoid any obstacle in the middle. Like the B, reach to the B is the reach part and avoid obstacle in the middle is the safe part. Yeah.
Cool.
Yeah, thanks. Yeah, and by the way, the value function is conditioned on perception. Yeah, that's why it's, yeah. Okay, questions? Yeah.
Thanks, Professor Schubert. I am particularly intrigued by one aspect that you mentioned about the OmniH2O. Like you mentioned that distilling the model makes the debug much more easier. So I'm interested in like what aspects do you think distillation makes it easier? Like in terms of, is it because of it's more interpretable or is it more
Yeah, that's a good question. I want to rephrase the question. It's like why like doing model-based control or integrating model-based control make debugging easier for humanoids, especially like something like OmniH2O? I think interpretability is one big issue because sorry, let me go to these slides. For design reward for OmniH2O, like it is some part is intuitive, but some parts you really do a lot of like hardware in the loop. Like basically you are doing graduate student descent. So you some graduate student design reward function and you observe what happens in real world and you take some gradient on the reward function, right? I mean it's not, you don't have like kind of like strong reasonings or like kind of like you cannot build like clear causality between what change you add in a reward to what change you have in the real world. Yeah, but again, if you do model-based, you have something you can directly leverage. For example, in this case, because you are solving a QP, right? You can quantify its error, you can quantify its performance, you can handling its, like things like that. Yeah.
So the distillation you mentioned is using model-based approach instead of
Yeah. I mean, the simulation in this case is just standard, SFGM simulations, like GPU accelerate simulators, yeah, which is basically a black box and kind of like simulator, yeah.
All right. I think I'll maybe ask one more question.
Yeah,
It's
sure.
very nice you talk about, I think, 3 different you know, perspectives, you know, how to combine this learning-based and model-based approach, right? And from your perspective, does, you know, any of these 3 is, you know, you think is more critical than the others, or it just depends on, you know, different robotic system or different tasks you want to achieve? You know, I think we have a lot of people trying to explore this, you know, intersection. Any thoughts?
I think that's a very good question. I don't have an answer for that, unfortunately. I think it really depends on what is the bottleneck in this problem. So if the bottleneck in the problem, for example, in drone, why we do learning dynamics in this case, because you cannot simulate aerodynamics. You need to solve a Navier-Stokes equation. You don't want to do that. And also, it's relatively easier to learn because it is a smooth function at least, right? We know that the physics in this case is smooth, it's continuous. And also, once we learn F, we know how to do controller. We can literally just do adaptive control or feedback linearization. You know how to handle controller even though you learn a model. And that's why we choose to learn the dynamics here. But in Laggy robot, for example, if you cannot directly learn a model, if learning policy is easier, you probably want to do the second one, third one. Yeah, I think it really depends on what is the bottleneck in the problem. If the bottleneck is the modeling, right? If the bottleneck is the RO, like exploration, or the bottleneck is just the optimizer, right? So, yeah.
Okay, all right. If you have more questions, you know, please join the lunch with our speaker. So let's thanks Guanya for the excellent talk again, and I'll see you.
Thank you so much. Yeah.